Hello everyone, welcome back to Bytes of CAC, and we are on the part 2 of K nearest neighbor algorithm. And in this part we are going to discuss how K changes the classification decision and how to find the optimal K the usual way, and one of the very popular method is used by researchers nowadays. So as I wanted to see how the value of K affects the decision making, I made this synthetic data set. It's a very random data set you made using scikit-learn. So this was a piece of code where I used three clusters of data, and each will have two features, and there are 500 data points in total. And then I have split the data into train and test points. 80%, that is 100 points, are kept for the test set, and 400 points are kept for the training set. And I have just plotted, I've just made a scatter plot of the data, and this is how it looks like. So this is class 0, that is how implicitly they have classified. This is class 1 and this is class 2. That is, the yellow is class 2, the blue is class 1, and this violet is class 0. So I have considered a test point. This is the test point, which has been marked as red. Now, if you're wondering how could I guess that this particular point belonged here, this is, of course, looking at this point, you know why I have chosen a point like this, because this point is equidistant, at least visually equidistant, from both this point, and this point actually sits in between this cluster and this cluster. So this was a bit of a trial and error. I actually had to go through different test points to find out which one will suit my need. So this was a point that suited mine. Now, if you want this, if you are interested in this particular notebook, do leave me a comment. I will share. Anyways, so let's move on. So I wanted to find out the class of this particular data point when the number of neighbor is 1. So that is how I wanted to know that if it is nearer to the yellow or nearer to this blue. And it said that this belonged to this blue cluster. This belonged to this blue cluster. Now when I took the number of neighbors as 3, it said that it belonged to the yellow cluster. Then for 5, it was again yellow. For 7, it was again yellow. For 21, it was yellow. And for 75, it was yellow. And I stopped for now. So when we are considering more number of neighbors, we see that it is consistently giving the answer that this belongs to the yellow cluster. Now what happens here is, when we consider the number of neighbors, it implicitly draws a sort of line between the clusters. This is not something mentioned in algorithm or anything, but using a particular plot, you can actually find out that it sort of draws some line between the plots, or some line can be drawn between, not the plots, the clusters, and based on that, they are making the decision. So this is for when k equals to 3. And if you look at the decision boundary, like everything that falls here, here, here will belong to this yellow class. Anything that falls in this blue colored zone will be assigned the blue, like this class 1, and anything that falls near the violet will be assigned this cluster. So when you look at this particular point falls somewhere here, the test point. So therefore, since it falls in the yellow zone, it has been assigned the value of 2, the cluster number 2. Now when we consider this one, that k equals to 1, now if you look at this decision boundary, it looks somewhat here, but when you are considering one neighbor, see, this blue has actually gone down a bit, and I think this is where the point belonged, and they assigned a value of like cluster number 1 or this blue cluster to this data point. Now see the change in the boundaries as I change the value of k. This is for k equals to 1. For k equals to 3, it looks like this. So this part is now covered by, like, blue has been pushed up. This has been replaced by this yellow line or the yellow zone. When k equals to 5, again, the yellow is like this. This was a very rugged kind of, as you can see here, it's a very rugged kind of a line, a very random kind of a line, complicated line. But this complication is bit less here, and as I increase the number of or the value of k, this line is getting straighter and straighter. See, for k equals to 100, it's almost a straight line. For k equals to 75, it was almost as, for 21, it was almost, but anyways, it wasn't really very straight, but kind of it was smoother than 1 or 3 or 5. So this is for k equals to 150, pretty a straight line, I would say. For k equals to 175, this part gets smoother even. See, this was a little uneven for k equals to 150, that is number of neighbors equals to 150. For number of neighbors equals to 175, this part is even more smooth, and I did up to 200, so it was almost smooth, quite a smooth line, right? So this is what it actually looks like for k equals to 1, 3, 5, 7, 21, 75, 100, 150. You can see the change. You can see the change in the decision boundary. So what happens here is, when this value of k is small, it results in a complex decision boundary where it captures too much local information. Whereas when the value of k is large, it gives a smoother decision boundary, but it overlooks important patterns in your data. So low value of k can give you overfitting, while a very high value of k can give you an underfitted thing. Now the point is how to choose the optimal value of k, because k depends on a number of factors. Number 1 is the dimension of the sample space, that is how many features in your data, the size of the data set, the covariance structure, that is the pattern of relationship between the different variables in the data set. So it depends on that. Then the proportion of samples in your data. So these are the points on which the value of k depends. So in normal day-to-day, normally what we do is we use a trial and error method kind of. So what happens here is, first of all, we select a range of k values from a random number to the square root of the total number of data points. That is the training data point mostly. Then we find out the error incurred by each of those k's, and then we plot the error versus k. So error is your y and this is your x. So this gives you an idea of how the error changes with the k value. And then what we do is we select the k with the lowest error rate. So that will, for the best fit and stability, we just select that from the plot. And this is how we do that. But in modern research, what is happening nowadays, the concept belongs to some 2008 paper, where all the neighbors of the test data points were used, and the nearest ones were rewarded and the further ones were penalized. So here they have actually bypassed the need for this k. They are not using like one neighbor, two neighbor, three neighbor. Instead, they're using all the neighbors, and depending on the distance, the decision is made. How is it done? In fact, these are the two papers, like this is a 2020 paper, this is a 2023 paper. So both have used this technique. So this is known as inverted indexes of neighbor classifier. Now you won't be needing to do that in your what shall I say, in your interviews and things like that. But it's better to know what researchers are actually doing with this particular, like how to find out this particular value of k. So what happens here is, this is your test point and this is the training data cluster. So first of all, they find the similarity distance or the distance between the test point and all the data points. Then these points are sorted in ascending order of the distance, that is lowest to highest, and the respective class is also noted while they are sorting. And then what happens is, summation of the inverted index of each class is calculated using a particular equation like this. What is happening here is, C is a particular class and LC is the total number of points present in that class. Now every data point is given some rank I according to the distance. Now since the points are sorted in ascending order, so lower the rank, lower the distance. But we are trying to reward the nearer points. So that is the reason why we are taking inverse of that rank. Because say for a number like 1, 2, 3, 4, 5, if we take the normal summation without taking inverse, so a further point, that is a point which has rank 3, which is the furthest among all these 3 points, will carry more weight in this equation. But 1 by 1 is always greater than 1 by 3. And in fact, this is what we want. We want the further points or the furthest points to have a lower impact on this summation for a particular class. So this is the reason why we are taking inverse of this I. Now we calculate the probability of the test point belonging to the class C as Px given C as Sc by S. Sc is you get from here, and this is how you get S. N is the total number of points. Just remember this, LC is the total number of points belonging to a particular class C, whereas N is the total number of data points irrespective of the class, and I, as I said, is the order of the data after sorting. So this is how the probability, and obviously whichever C has the highest probability, that point will belong to that class. So this just negates, or this just bypasses the importance of k, or the necessity of inputting this value of k every time and just doing the trial and error thing and so and so. So this is how researchers use find out the optimal value or the true value of a class depending on whatever training data they have. So that's all for today. Stay tuned for the third part. Third part will be hands-on, and of course some here and there, whatever that is left of KNN will be discussed. Thank you for watching.